In this video, I'm going to talk about a Fourier series for even and odd functions. The integration, before talking about the Fourier series of even and odd function, I'm going to talk about the integration of an even and odd function over interval from negative L to positive L. The reason is that the integration of even and odd function can appear in the computation of A0, AN, and BN, because for a periodic function, ft is Fourier series given by A0 plus summation n from 1 to infinity an cosine n pi t over L plus bn sine n pi t over L. Now the A0 is given by integration 1 over 2L integration from negative L to L ft dt, and an is 1 over L integration from negative L ft cosine n pi t over L dt, and bn is 1 over L negative L ft cosine n, this is sine n pi t over L dt. So here n is from 1 to until infinity. So we are looking at integration of some functions, okay? And also we know the cosine is even function according to the definition of even function that I mentioned in the previous video. Sine function is odd function, okay? Alright, so now a lot of time we have to do the computation integrations. If we have some way to simplify the computation, it would be great. That's why I look at the integration of the even odd function first. So for even according to the definition of integration of function ft, for example, the integration of function ft is given by is basically computed the area covered by the function below the function or above the function if it's a negative, okay? So here ft, let's say ft is odd function over here. So which means ft, this is positive. If for some t the ft is positive, for negative it becomes negative. That's why it's sort of you do this shape, because if this is positive it's going to negative, if this is positive it's going to negative, okay? So according to definition of integration, so it's just integration of this the area underneath from 0 to L. For example, this is the area, is a plus sign, so which means I'm gonna calculate this area, and I'm also going to minus the area from the bottom side, this side. This is the area covered by the orange color over here. So actual integration of a negative L of ft over dt is the area covered by red, the red area, part minus the area of this orange color. So that's what the integration means. So if we have odd function, if ft is odd function, which means whatever value we have, for example, whatever value I pick at this t, I got this point over here, this area, this will be the same. If I do the negative t, this is the t, this is negative t, it will be the same size, which means if I'm going to do all the integration, the size of the two, they'll be equal, which means the area will be the same for both above this t axis, they'll be the same, above and below they'll be the same. That's why the integration of this odd function is 0. So I want to say that is negative L of odd function is always equal to 0 over dt, of course, equal to 0, okay? Similarly for the even function says, okay, if I have a function, I use the same concept, it's the area. Let's say assume that from 0 to L, my ft is always positive, okay? So according to the even function says is ft, so ft is f negative t. So if you put the negatives from left hand side from 0 to negative, it also is positive. Of course, for odd function is a little bit different, which means ft is negative f negative t, okay? So which means, hey, if this is positive, area is positive, this is also positive. Of course, if this is negative, this is also negative. So which means the integration of negative L ft over, let's see, this is the dt over here is the area of the right hand side, okay, represented as plus of r plus the plus of L, which is the area of the left hand side plus the area of the right hand side. when ft is even, this right hand side, the area of right hand side is the same as the area of left side, because for any t over here, for example, if I do a t over here, for example, if I compute the area over here, this is t. If I do the same negative t over here, there will be the area will be the same. So if you do the integration over the entire space, entire range from 0 to L, the area is the same as the area from 0 to negative L. That's why they are the same. So the integration of negative L of from negative to positive L of even function ft is just twice of integration of ft over dt from 0 to L. It's twice of that. Okay, that's the property for the even function. Okay. Now let's see. Now let's take a look at what is the Fourier series for odd function. Any based on this property I mentioned over here, anyway you can simplify the computation of the Fourier series for even odd function. So let's here say, hey, if ft is an odd function and also is a periodic with a period, a general period of 2L. Okay, we want to see if there's any way we can simplify the computation of a0, an, and bn. Okay, so according to that, in the previous slide, previous video, I talked about how to write a function, a general function into the Fourier series. So ft is, as I mentioned over here, right over here. So ft is a0 plus summation from n is 1 to n is infinity of an times cosine n pi t over L plus bn times sine n pi t over L. So that's the general form for the Fourier series for a general periodic function with period 2L. And here let's take a look at what's a0. So a0, I already mentioned over here, this is how we compute a0, an, and bn. Okay. Now since the ft is an odd function, we can see if we can simplify the computation of those parameters. Let's see a0 is given by integration of 1 over 2L, integration of negative to L ft over dt. Now we can use the property. As I mentioned before, because ft is odd function, right? Odd function means the integration of odd function from negative to positive L is 0, which means, hey, this is 0. I don't have to calculate it, right? Doesn't matter what function you have for the ft, the integration will be 0, as long as it's an odd function. So yeah, done. That's easy. We got a simplification of the a0. a0 always 0 for odd function, odd period function. How about an? So an is 1 over L integration of negative L to positive L ft over cosine n pi t. Okay. So first of all, ft is odd function, as I assumed over here, and cosine n pi t over L. This is the even function, right? So according to the property of even odd functions, the odd function time even function is still odd function. Okay, so this is the property I mentioned in the previous video. Talk about property for the even odd function. So because this is still odd function, the integration will still be 0. Okay, I don't have to worry about it in the other computation. It's just 0. A is still 0. And bn is 1 over L from negative L and L ft sine n pi t over L dt. So here ft is odd function based on assumption, and sine n pi t over L is odd function. The odd time odd is even function, as I mentioned before. So this bn, because it's an even function, so this one integration from negative L is just twice of integration from 0 to L of the same function over dt. Okay, so I can pull this 2 combined with 1 over L. So it's 2 over L integration from 0 to L ft sine n pi t divided by L over dt. Okay, so that's the way for. So this is the way how you can simplify the whole thing. For the even function, the a0, a1 until anything, they're always 0. They're always 0. The reason you can also say here, because you can also interpret it this way, because ft is odd. Odd, of course, your right hand must be odd. This one must be odd, right? So that's why any all even component has to be 0, which means a0 a0 is constant, so this is the even one function. This is also even function. Of course, you cannot. There has to be 0, right? So only this guy is not 0. Okay. Similarly for even function ft with period 2 pi. Okay. With a period it's period 2L. Okay. So we can also figure out the how can simplify the computation of the parameters a0, an, and bn. So again, the format of ft, the Fourier series is always the same. It's a0 plus the summation from n equal to 1 to n equal to infinity of a n cosine n pi t over L, bn plus bn sine n pi t over L. That's the same thing. So here a0 is 1 over 2L integration of L from negative to positive ft over dt. So here ft is even, not odd anymore. So the integration from negative to L is just twice of it, from 0 to L ft over dt. So we use 2 cancel out this 1 over 2t from the denominator. So it's 1 over L integration from 0 to L ft over dt. And an is 1 over L integration from negative L to positive ft times cosine n pi t over L over dt. So ft is even, cosine is even, so even times even is even. Okay, so that's also property of the even odd function mentioned in the previous video. Now the integration of that one, because this is an odd function, so this has to be 0. The even function, so it's like 2 over L, because twice of that, 2 over L integration over 0 from 0 to L of ft times cosine n pi t over L times over dt. Okay, for Bn is 1 over L integration from negative L to positive ft sine n pi t L over L times dt. So here ft is even, sine n pi t over L is odd, even times odd is odd. So the integration of odd function over from negative L to positive is always 0, so which means Bn is 0. Okay, that's why I can simplify a lot in the computation. Okay. Now let me go over one example, show you how we can use the property to simplify a lot of computations. So let's say here ft, I give you a periodic function, which is also an odd function ft, which is given by ft is equal to a when t is within 0 and L, and ft is negative L when t is from negative L to 0. And this pattern will repeat with a fundamental period of 2L. So this left shows a picture of this ft looks like. Okay, so it's from 0 to, this is L, this is 3L, so this is 2L, this is 2L, so this is 0, this is negative L. So this pattern, you saw this is a pattern looks like. Okay, so the period, fundamental period is also 2L. And I want to show you that all of my A0, A1 until A infinity are in its Fourier series are all 0. Okay, so this is fairly straightforward. Okay, so according to what we know about Fourier series, the Fourier series of t is given by a0 plus summation n from 1 to infinity an cosine n pi t over L plus b in sine n pi t over L. So if I compute the a0 is over 1 over 2L integration from negative to L ft over dt and 0. So here ft actually is odd function, because this is ft for this one is ft is negative f negative t, right? So this is odd function. So the odd function integration will be just 0. Okay, so an is 1 over L integration negative L ft cosine n pi t over L dt. So ft is odd function and cosine is even function. So the product is odd function. So the an is 0, which already shown. Now we already showed that. We can also compute the Bn. Bn is 1 over L times negative over L for ft sine n pi t over L dt. So ft is odd function and sine n pi t is odd function, which means the product is, this one's be even function. So even function, the integration will be just twice of the integration from 0 to L. Okay, so 2 divided by L, I just combine 2 with 1 over L, is 2 over L. Integration from 0 to L, ft sine n pi t over L over dt. Okay, here ft is just a. Okay, it's defined here a. So now we have to do the integration. So basically, we do the integration of that part. So it is integration. If you do this one is 2, I can move this a outside, is 2a over L. The integration of sine n pi t over L over dt is L times n pi, L divided by n pi times negative cosine n pi t over L, because the derivative of cosine will be just sine, okay. And evaluate the 0 to L, so which is this L will be cancelled out. Okay, this is 2a over n pi times negative n pi. We evaluate that, so when L equal to t equal to L is cosine n pi L divided by L will cancel. It's just negative cosine n pi. This is a minus cosine, when it's 0 is minus cosine. This is a minus cosine 0. So this is a This is 1. So minus 1 is just plus 1. That's why this is plus 1, which is 2a over n pi times 1 minus cosine n pi. So that's my Bn. So actually the Bn, the function, the Fourier series for the function ft is given by summation from n from 1 to infinity, because all my a term, a0, a(n), they are equal to 0, right? So only term is here, right? So it's summation from n from 1 to infinity 2a over n pi. Just have to replace this one. 2a times n pi 1 minus cosine n pi times sine n pi t. Well, don't forget about this part. This is remember we still have here. Don't forget this is the Bn. So this part is my Bn. Okay. Okay, now I want to talk a little bit about a Fourier series for a function ft defined in a finite region. Doesn't mean it's a periodic function, right? Let's say, for example, if I give you ft, which is just defined in the area of a and b. Okay, let's say start from a to b, they're all positive, for example. If I want to find a Fourier series or any sine or cosine functions to represent this function, can I do that? Yes, you can also do that. It doesn't mean you have to have a periodic function. You can also have just define in a finite region. So what we can do is we can create, even if this is not periodic function, because we only know how to write a periodic function into its Fourier series, into basically the sum of sine and cosine functions. So what we can do is we can just do something. For example, I just make it a periodic. Of course, I want to use the nice product of even odd function, especially for odd function, to simplify the process. What I do is, hey, I can do, for example, if you define, this is a function defined from a to b, right? The function ft. So I can add a component from 0 to a, okay, all right, over here. And also I can do a negative, like this portion here is negative f negative t. So this function, I make it an odd function, which means this guy going to the negative side, I flip it to down. This one also flip it down this side, and then I make it just repeat the same pattern. You sort of make the period to be just 2b as your fundamental period. Then for this guy, you can define, for this one, you augment this. First one, you create a period function by adding actual self-defined pieces, like I mentioned here. Define a piece here, piece here, piece here, and you repeat these patterns. And then I can compute a Fourier series for this periodic function, right? This also is an odd function. This also is an odd function, right? Odd function, so the period is 2b, basically, right? So I can compute a Fourier series for a period, like I mentioned before. And also because the odd function, so the computation only depends on this. Only depends on the Bn. So a0, an, they are always equal to 0, right? Then I just have to restrict to find this one for this ft. I just have to restrict the point in that region, right? Once you fit a function, you just define this function in that region. Now you are done. Okay, so this one you can also write any function defined in any region into the sum of sine and cosine functions. Okay, so you can use a lot of property about sine and cosine function to simplify a lot of subsequent computations.